In this video, we are finally going to learn the method of U substitution, which is what we have to do if we have a function that would require product, quotient, or chain, and there's no way of rewriting it. So it's kind of just the reverse of chain rule. Remember, when we apply chain rule, we first leave the baby inside, and then we multiply by whatever its derivative is. So this is kind of what we're looking for when we're integrating. We need to find a part of the function whose derivative is also in that function. So the nice thing is this is the only method we're learning. So once you get the hang of it, it's just we're repeating the same process, and it becomes easy because we're going to do it a lot. So first step, we're going to choose a substitution for u. So we want to rewrite the integral so that it looks a lot easier. And you want to pick something that kind of looks like a baby. So pick an inside function, or maybe even a denominator. Denominators are definitely helpful. If there looks like there's two inner functions, choose the one that looks the most complicated. And then we want to rewrite that function in terms of u. And this is probably the most confusing, difficult part, is that your notation has to be accurate, and we'll talk about it when we get there. You're going to integrate your new problem, and we don't want u's in our answer. So if we're using an indefinite integral, which we have no numbers here, we're going to have a plus c, and this can't be a u. So we may have to plug our u back in. If this is a definite integral, then we will have numbers up top and bottom, and our answer then is a number. So there's no reason to ever go back and plug u in. And again, we'll get there. Okay? So let's go ahead and just start right in with an example. When I look at this, we have chain rule here, we have product rule, and those are not allowed in integration. So we must rewrite this function. And so what we're going to do is we're going to choose a variable to represent the complicated function. And in this case, the baby is this guy here, and that's all we want to choose. So we're going to choose u to equal x squared plus 1. And we're doing that so that this can come out and u can take its place. So instead of that function to the second power, it's now u to the second power. And that's a much simpler function to integrate. If we change the problem to u's, we can no longer keep dx here. We then will need a du. Well, in order to find du represents the derivative of u. So remember, we were taking derivatives, and this would be like the derivative of u with respect to x is equal to 2x. I just took the derivative of the function called u. If I were to take this guy to the right, I see that the value of du is equivalent to 2x times dx. And we're going to need this because I have to do something to swap this dx out. I also can't leave 2x and bring it down. I can't have a u and an x in the same integral. The nice thing, though, here is most of these are set up in a way that everything has an easy substitution. So we still need to swap 2x dx out for something in terms of u. And we just so happen to see right here that 2x dx is equivalent to du. So it can go out, and du can substitute in place. And now I have a nice, pretty integral. All my variables are corresponding, and now I can integrate. So when I integrate, remember, we're going to add 1 to the exponent, and we're going to take that original coefficient and divide by our new exponent. Since this is an indefinite integral, meaning no upper and lower bounds, we do need our plus c. And this would be the answer, except for the fact that we don't want to see u's in our answer. So if it's an equation, we do need to go back and replace the u into our function. So 1/3 times x squared plus 1 to the third power of c. And the way we can check our answer is the same as we did before. We could take the derivative of this. So if I were to take the derivative of this function, this 3 would come down, baby stays inside, and it's now to the second power. Then we multiply by the derivative of that baby. And since this is a constant, his derivative is 0. And do you see how the green here matches the integrand that we started with in the original integral? Okay, so that's how you can check to make sure that blue answer is correct. Okay, so let's do another problem. In example B here, we also must use U substitution because trig functions are only allowed to have a single variable. So 4x is the problem. So I'm going to choose that to equal a single variable. Remember, I'm going to have to turn this into du, which represents the derivative of u. So the derivative of u is 4 dx. Remember that dx is down here, and I'm multiplying it to get it to the other side. So now I'm going to use the process of u substitution to make my problem easier. Okay, so cosine of 4x becomes the cosine of u. All I did is swapped out 4x and replaced it with a u. So this is now taken care of. I still need to replace the 4 and the dx, and I just so happen to have that right here, and I know that's equivalent to du. So I can make a substitution. I can swap out the 4 and the dx and replace it with du. Now I have a nice function that I can go ahead and integrate. Remember, sine and cosine are derivatives of one another. Derivative of sine is just cosine, so we don't need to mess with any negatives here. And then finally, don't forget we have plus c. And just remember, if your answer has a u in it, you do need to go back and plug in u. So it's the sine of 4x plus c. If I take the derivative of this, I'll get the integrand that I started with. Okay, so again, another example here. We have to use u substitution because here we have product rule, we have chain rule, and no way to rewrite it unless we wanted to cube that function, which would be really ugly. So let's choose this to be u because that's my innermost function. Again, we're choosing u as like a baby. So then du is the derivative of whatever you picked. So du in this case would be 2x plus 0 times dx. So when I go ahead to make my substitution here, this swaps out, u swaps in. So this becomes u to the power of 3, but I still have an x and a dx that I need to replace. So if we notice down here, we have x dx, but we have this 2 that's kind of in our way. Well, this is an equation. And in an equation, I can rearrange it by doing inverse operations. So I'm going to go ahead and I'm going to divide each side by 2 so that I get 1/2 du equals x times dx. And that's helpful because now this matches what I wanted to eliminate up here in the problem. So I'm going to substitute in a 1/2 and a du. And don't forget, if I have coefficients, they can be rewritten in the front of the integral. So I really have 1/2 u cubed du. And so now when I go to integrate, again, I'm going to add 1 to that exponent, and then I'm going to divide. So here I'm going to divide by 4, which is going to give me 1/8. I also have plus c. And then don't forget, we don't want to see a u in our answer, so we do need to go back and plug in whatever we chose for u back in the beginning. And this would be your final answer. The next couple examples are actually we'll save for the next video.